Welcome back to our session on analysing information transfer in complex systems. In this final short video, we're going to look at multivariate and conditional approaches to the transfer entropy. All the ways we've looked at transfer entropy as our primary measure for information transfer before have considered single sources only, or what we call pairwise transfer entropy. And yet, kind of hanging around in the background, in our diagrams, we've had multiple information sources to the target represented. So the big question is, how do we handle that? We've only talked about pairwise approaches, single source approaches before. How do we move beyond that to look at multivariate source approaches? Well, we're going to start by considering the conditional transfer entropy, which looks at how much information about the next observation of the process can be found in some source Y in the context of not only the past state of the target, but also an observation of another process. So here in our diagram, we can see our two processes. So now we're going to consider the information contribution from our source node in the context of not just the target past, but this other source node as well. Mathematically, this is simply done by adding that other source node, here in the mathematics Z, into the conditional part of our conditional mutual information value. Apart from that, it's almost exactly the same as the transfer entropy, and so that's why we call it the conditional transfer entropy. Notationally, we're looking at the source of the target in the context of another source as well as the target past. Okay, that's all it is. Otherwise, everything else looks the same. We're still looking at having an embedding dimension on the target past. We can think about embedding the source and the conditional too in similar ways with similar considerations that we've had in the previous short videos for this session. Similarly, also, we can have a local or pointwise conditional transfer entropy represented here. Again, it looks almost exactly the same, except that we have our conditional here too now. In fact, all the considerations that we've gone through already for transfer entropy, the pairwise version can be applied to the conditional version here as well. We can add in source target delays. We can add in delays from the conditional to the target. We can add in different embeddings on the conditional. We can add in multivariate conditionals as well. Here I've only drawn a single conditional Z. We could have a set of conditionals that we're considering here as well. All of those are basically in the style of such extensions for the transfer entropy that we have already considered. The big question then is, how does the extra conditioning on our other source Z change the transfer entropy? Well, the change could be in a number of ways. One change is that it removes redundancies between the source Y and the conditional Z in the same way that the conditional mutual information conditioning on some other source Z removed redundancies. This can include common driver effects. Here, for example, if we looked at it, we may see a transfer between Y and X if we just look pairwise, but if we look conditionally on some common driver, we may no longer see a driving effect from Y to X. So that would be the removal of redundancy between Y and the common driver Z. Similarly, pathway effects can be clarified using the conditioning. Here, if we just look at a pairwise transfer between Y and X, we may see something very strong due to a Z on the path, but if we condition on Z, we may say then that there is no transfer from Y to X conditioning on Z. So again, that would be a removal of redundancy by the conditioning on Z here. Of course, we could include synergies between Y and Z, as we know the conditional mutual information can do. Here, for example, this could include some kind of gated effect, like an exclusive OR function between Y and Z having an outcome on X. We may only detect that if we're conditioning on the other variable Z here. Now, all of these seem to be very positive effects at first, regarding the extra conditioning on Z here. So this starts to beg the question, do we actually need both the pairwise transfer entropy and the conditional transfer entropy? Or do we need just one, maybe just the conditional transfer entropy? It's a very important question. I want you to ponder that yourself before you look in the next slide at the answer that I'm going to give you. So to address that question, I want us to come back to think about our goal here, which was in modeling the information processing in X to create an information regression about that information processing. To do so, let's go to a simple two-source case. We can see the mathematics for the general case in my paper from 2010 below. So here, let's think about our regression is basically trying to account for all of the information in our target. And the first thing we do, as you know, is we look at our active information storage, how much information came from the past. And then we can look at how much information comes from one of the sources as a transfer entropy. And what's left after that is a conditional entropy. What's left, the uncertainty that's left in that target, given the target's past and our source variable. Having done that, we can then take another step and we can split out that remaining uncertainty in the target into now a conditional transfer entropy from Z to the target given Y as a third step in our regression. And that then leaves us with a remaining uncertainty in the target given the target past and our two sources. Okay, so we can now see how the conditional transfer entropy starts to fit in with the pairwise and the active information storage. Now, importantly here, the way we've run this regression is to look at source Y before source Z. Now, when we considered doing the storage first before the transfer, we made a very principled choice to look at it in that way. We've discussed that at length. But here in choosing between Y and Z, is there a natural choice of which one to consider first? Or could we do it the other way? We could look at Z first and then Y. And they are equally valid. There certainly doesn't seem to be a natural preference of one over the other. There are exceptions to that, which I'll talk about in our next session. But for the time being, we can consider them as both equally valid approaches here. So which way should we do it? And does it make sense to have two different ways to do that? Well, I think the first thing to point out here is that we do have something that's invariant. We can look at the collective effect of those two sources together on the target in what we call the collective transfer entropy. This is simply the sum of the pairwise transfer entropy from one source plus the conditional transfer entropy from the other. Okay, and this is, for our purposes here, it's definitive. There's only one way to do that. There are multiple ways to break it down, though. It doesn't mean that one's more correct than the other. It doesn't mean that it's not okay to have multiple ways to break it down. What we can consider here is that we have multiple perspectives. Okay, or indeed, these are two different models, modeling subcomponents of the total information transfer contained in the joint or collective transfer entropy here. So to return to our question of whether we indeed need both the pairwise transfer entropy and the conditional transfer entropy, I would say that we do, because they are both important parts of the total information transfer that we see here. Okay, the conditional transfer entropy alone doesn't tell us everything. If you only looked at that, you would miss these important pairwise components. So even though it seems to have many advantages in terms of removing redundancies and adding synergies in, if you only look at them, you are going to miss these components in the total information transfer. So my answer is that they are both important components. They are both submodels of a whole model here. So we can look at computing the conditional transfer entropy in JRDT as well. We have that available in the autoanalyzer. And again, as per the transfer entropy, we have all types of underlying conditional mutual information estimators available. with similar parameters for those underlying estimators and features, including the ability to run statistical significance tests, to do local or point-wise computations, and so on. Let's just have a quick look at that. So I'll start the auto analyzer here. I'll pick the conditional transfer entropy. What we can see here is we have an additional field, the conditional column in the data, the one to condition on. And we have these fields here, the conditional embedding lengths, conditional embedding delays tau, and delays between the conditional and the target. If we hover on those, again, they'll tell us exactly what they are. So we can set them just the same way as we did the embedding length k for the target embedding and tau, and the source target delay there as well. To run a quick computation, we could pick out the heart rate, breath, and blood oxygen interaction, and let's just leave the parameters as default and run a brief calculation there, and we'll see that we get our result nice and easily, and the code generated as before. Okay, so that brings us to the end of our session on information transfer. We've looked at the philosophy behind information transfer and how it relates to information storage together in analyzing information processing in complex systems. In particular, we've looked at transfer entropy as a model for information transfer in this wider perspective of distributed intrinsic computation. In particular, we've focused on measuring information transfer via the transfer entropy, and we've looked at how pairwise transfer entropies and higher order transfer entropies are related. We've also looked at how to use the JRDT toolkit via the auto analyzer and extensions of the code it provides to analyze information transfer in complex systems data sets. Coming up in our next session, we're going to look at inferring effective networks from time series dynamics. How can we form a network model if we've just got a multivariate time series? How can we use these measures to form a simple model that would explain those dynamics?